the symbolic predicates that the inputs have to satisfy to follow that path. Right? So in this particular application, the symbolic exploration doesn't play a large role, so I won't describe the implementation of these components, but they play a key role in a lot of our other applications. And again, you can look at the website for more information. So the first thing I'll talk about is this static analysis component, which we call Vine. This is sort of a high-level overview of Vine, and Vine is split up into a platform-specific front end and a platform-independent back end. And then at the core of Vine is this intermediate language, which we've developed to be small, but also flexible in that it can accurately represent the different types of assembly languages that our tools use. So then in this architecture, instructions from a binary program are translated to the intermediate language by the front end, and then all back-end analyses are done on this intermediate language. So this is convenient and allows very powerful analysis because we can write program modules to do various types of analysis without having to deal directly with the complexities of an instruction set like x86, right? This design also allows for really easy extensibility because we can write new analysis systems on top of the existing ones. And so we provide a sort of core set of components we see here. And then we can write new analyses without having to sort of reinvent the wheel and abstract all the low-level details away and focus just on implementing whatever solution we're interested in. So next I'll talk about the dynamic analysis component, again, which is called TEMU. So TEMU is this whole system analysis platform which we've developed as an extension of the open source emulator QEMU. Okay? And so we can run an entire system, including the OS and the program that we want to analyze, within this emulator, and then observe in a very fine-grained manner how the program is running and interacting with the system. So this whole system approach has a couple benefits. First, for a lot of security applications, we need very fine-grained, that is at the instruction level, fine-grained instrumentation on binary code. So because we are the system here and we're the ones who are dynamically converting the emulated code, we can very easily implement instrumentation. Right? Another benefit of this is that the whole system view gives us access to the internals of the operating system, so we can track operations in the kernel, and we can also observe interactions between multiple processes. So lots of existing analysis tools only give us a very local view, that is, they use them to analyze just a single user process. But this is sort of not complete, and our tool is more powerful because lots of attacks involve multiple processes, right? And attacks on the kernel, like rootkits, are becoming increasingly popular. So our tool can easily handle analysis of these types of attacks. So we have this system, and we've implemented a couple modules to help with our analysis. The first one I want to talk about is the semantics extractor. So for any given instruction that's executed by the program, we want to know information about, for example, which thread it came from, which process it came from, which module it came from, right? Or oftentimes code is dynamically generated and executed on the heap. So we want to have a mapping between addresses in memory and modules that are used by the system. Right? So the semantics extractor is responsible for collecting all this information, and then it passes it back up to the TEMU layer. And the actual implementation of this semantics extractor depends on the operating system we're running. So for Windows, we've developed a kernel driver that registers a couple callbacks to track process creation and memory allocation and that kind of thing. And then again, it passes it back to TEMU through a predefined I/O port. And for Linux, it's a little easier because we have the source code, so we know what the kernel data structures are, and we know the addresses of the relevant symbols, so we can just read this information from the outside, right? The other component that we've developed specifically for TEMU is a taint analysis engine, which we use to perform dynamic taint analysis. And I'll show on the next slide sort of how that works. Finally, we have this interface for TEMU that allows users to very easily extend the functionality and write their own analysis modules, which we call plugins. And so plugins can be loaded and unloaded at runtime to perform whatever analysis the user is interested in. So this whole TEMU system is implemented in Linux, and currently we can use it to execute and analyze code on Windows XP, 2000, and also Linux systems. So taint analysis, or at a high level, taint analysis works by where we taint all the inputs to a program and then track how the taint propagates as the program executes. So I just mentioned we have this plugin interface. The plugins are responsible for introducing taint into the system because where the taint comes from is an application-specific decision, right? So once the data is tainted, then the taint analysis engine monitors all the instructions that operate on that data in order to figure out how to propagate the taint. So it tracks all data movement operations, right? I want to point out this is a data flow-based taint propagation policy rather than a control flow or implicit flow-based one. So we maintain a shadow memory that stores the taint information for every byte of physical memory and bytes on the hard drive. And a benefit of using this is that we can actually track taint through data that's been swapped out or data that's been written to a file and then read back in. Right. And so finally, taint analysis works by checking how the tainted data is actually used by the program. And again, this is application specific, so the plugin determines where to check the taints and which taint syncs to hook. So that's the overall architecture of BitBlaze, but I haven't really talked about how that helps us to analyze crashes, right? I showed you some cool applications, but what do we do? Once we have this system, how do we actually use it to help us understand why a program is crashing? Well, let's look at what we have. We have this whole system emulator, right? And we've written a plugin called TraceCap, which outputs a couple files. The first file is an execution trace file, which is essentially a list of all the instructions that are executed by the program under analysis, as well as the contents of all the registers and memory used by each instruction. And the taint file also the trace file also maintains the taint information for every byte. TraceCap also outputs a state file, which is essentially just a memory dump of the program at the time of the crash. And an allocation trace file, which is a list of all the memory allocations and deallocations used by the program. And it collects that by hooking calls to malloc and free. So once we have these files that give us a whole bunch of information about the behavior of the program that we're analyzing, what do we do with them? Well, we've developed different tools to perform different types of analyses on these files. And I'll go over some of these tools on the next slides that we use for this specific application. So, right, I mentioned trace files contain detailed information about every instruction that was executed by the program. And so we have a whole bunch of instructions, and what do we do with that? Well, the trace files are stored in a binary format. So we have a tool called TraceReader, which parses this file and then outputs it as text. And we can tell TraceReader to disassemble just a specific region of the trace, or maybe even just a specific instruction if we want a more local view. Right? And as part of the output is all the information we could possibly need about every instruction. So, for example, we maintain a sequential index into a trace that uniquely identifies every instruction. We print out the EIP of the instruction as well as the disassembly. In this case, this instruction is operating on memory. So one of the operands that we print out is the address of memory as well as the contents. I also mentioned we have taint information in these traces. So in the case that the instruction is operating on tainted data, we tell you what that tainted data is. So every taint entry is a pair of integers. And the first integer is an ID that tells us the taint source. So where did this taint come from? In this case, we assign ID 1111 to the tainted input files. This means this came from a file, and the byte that was used to taint this particular value came from offset 5 into that file. We also have various process level information, thread IDs, as well as processor level, for example, condition flags and the raw bytes. So that's how we actually read trace files. But we haven't done any real analysis yet, right? So lots of times we're interested in just at some particular point in the program, we want to know how this particular byte got set, right? So we have this huge trace, and a lot of times it's not feasible to look through every instruction. So a slice of a program, a variable in a program, is a list of all the instructions that might influence a particular value. So we have a tool, x86 slicer, which computes a data flow-based slice of any variable at any arbitrary location in the trace. And the output looks something like this. So in this case, we're slicing on variable AX. And we can look at this instruction and say, well, the value of AX came from this memory address. Well, how did the value at this memory address get set? Well, the next entry in the slice shows us. We pushed this value at that memory address. Well, where did the value of EDX come from? Again, looking further up in the trace, we can see, oh, well, we moved the value from the stack pointer into EDX. And now we have this sort of very focused view of exactly how the data propagated to get to this final state. And this is a relatively simple example, but hopefully it illustrates the point. So in these applications, we have actually two different trace files. We have one trace file which was collected using an input that caused the program to crash, and then we have another trace file which was collected that didn't cause the program to crash. So oftentimes it's helpful for analysis purposes to be able to establish a correspondence between instructions in the two traces. And to do this, we use a tool called trace-align. So what trace-align does is it walks through the traces and computes an index for every instruction. And then alignment comprises essentially matching indexes across the two traces. And then we can print out regions of the trace for which the control flow was identical in the two traces and where the two traces diverged in their execution. So we can see here the traces starting from the beginning up to instruction number 1362 executed identically. And then they branched off somewhere at the disaligned region. So the first instruction in the disaligned region, as well as the last instruction in the aligned region, actually tells us a lot of information. This is why the two traces actually executed differently. So why does this help us? Well, first of all, we have taint information in the trace files, so we can print out, right, this particular branch that caused this divergence, right? We have a divergence because we have a branch for which the target was different in the two traces. Well, in this particular disalignment point, the target of the branch was computed based on a tainted flag. So this means that the original tainted input had some influence on why the programs were executing differently. So instead of just having to analyze an entire trace file, right, we can sort of look in at just a particular location, and oftentimes this tells us a lot of information about why the program is acting like it is. So that's trace alignment. So we have a memory dump and we have a trace file, and I mentioned, right, the trace files have taint information, but a lot of times we want just sort of a snapshot of memory at some location in the trace. Maybe we're not interested in exactly the instruction that operated on the tainted data, we just want to know what data is in this general memory area. So at any location in the trace, we can use the trace file and the state file on a tool called trace dump to actually output the contents of all the memory around any register that's acting as a pointer. So in this case, we can see we're using trace dump on this instruction, and this particular register looks like a pointer, and here's the contents of all the memory surrounding that. And we can see here this particular data is tainted. Okay, so a large class of vulnerabilities are related to dynamically allocated memory. So I mentioned we have this allocation trace file, and we have a tool, allocreator, which basically parses this file, and it can tell us which allocation corresponds to any given address. So here we can see we run it on, well, at the top we run it on address 726.0020 hex, and it tells us it found one buffer, right? And so in this tuple here, we see at this instruction count, this is where this particular memory was allocated, and then it was never deallocated in the trace. That's why the N comes from, right? And that was the address and the requested size. We can also, if we're not interested in just a specific address, but rather some location in the trace, we want to know what are all the live buffers at this location in the trace. We can just feed this tool an instruction count, and it will print out all the buffers as well as the addresses. Okay, and finally, because we are actually looking at all the calls to memory allocation routines as well as frees, we can track when programs are freeing the same memory twice. And so the tool can actually print out what it thinks are double frees. And this could be useful for trying to find new vulnerabilities. Finally, the fact that a byte is tainted at any location in the trace is useful because it tells us that byte is somehow related to the original tainted input. But it doesn't really tell us how it's related, right? So for example, if we taint all the inputs that an attacker has control over, and we have some tainted register at a location in the trace, well, we know the attacker has some degree of control over that, in the value of that register, but how much control? So for this,